Welcome to this lecture on hormone receptors. Today, we are going to explore the fascinating cellular antennas that allow our bodies to translate floating chemical signals into precise biological actions. By the end of this video, you will understand both the biology and the mathematics behind how hormones actually work. To begin, imagine you are in a crowded, noisy room where hundreds of people are shouting different messages in various languages. If you only speak English, you will only react to the English messages and ignore the rest. In the human body, hormones are exactly like those shouted messages traveling rapidly through the bloodstream. Your cells are the listeners, but they cannot hear every single hormone that passes by. To listen to a specific hormone, a cell needs a special ear or antenna tuned exactly to that hormone's unique frequency. These cellular antennas are what we call hormone receptors. Now that we understand the antenna analogy, let us look at the formal biological definition. In scientific terms, a hormone receptor is a highly specialized protein molecule. These proteins can be located either on the outer surface of a cell membrane or deep inside the cell's cytoplasm or nucleus. When a specific hormone, known scientifically as a ligand, encounters its matching receptor, it binds to it with incredible affinity and specificity. This binding event acts exactly like a key turning in a lock, which then triggers a complex cascade of chemical reactions inside the cell. Building on that lock and key mechanism, it is important to note that receptors are highly selective. This means a thyroid hormone receptor will only ever bind to a thyroid hormone and absolutely nothing else. This prevents crossed signals in the body. Furthermore, the relationship is not static. The number of receptors on a cell can dynamically increase or decrease based on the body's needs. This dynamic adjustment allows the cell to become more or less sensitive to a specific hormone over time, ensuring our physiological responses are always perfectly balanced. So, why do these microscopic structures matter so much in real life? Simply put, without receptors, hormones are completely useless. They would just float in the blood forever without causing any biological effect. For example, in a medical condition called androgen insensitivity syndrome, a person produces plenty of male hormones, but their body lacks the receptors to detect them, leading to female physical characteristics instead. In modern medicine, many life-saving drugs work by either blocking these receptors, like beta blockers for heart conditions, or stimulating them, like synthetic insulin for diabetes. Having seen their clinical importance, let us now explore the beautiful mathematics of their binding. This relationship is governed by the laws of chemical equilibrium, similar to puzzle pieces snapping together and falling apart. The formula shown calculates the dissociation constant, Kd. Here, H represents the concentration of the free hormone floating in the blood. R stands for the concentration of free unbound receptors. HR represents the active hormone receptor complex doing the work inside the cell. Finally, Kd tells us how easily they let go of each other. A smaller Kd means a very high affinity, meaning they stick together tightly. This mathematical foundation leads us to a second crucial formula, which calculates Y, known as the fractional occupancy. Fractional occupancy simply means the decimal percentage of total receptors that are currently bound to a hormone. In this equation, H is again the hormone concentration, and Kd is the dissociation constant. If the hormone concentration increases, the fraction of occupied receptors also increases, approaching a maximum limit of 1, which represents 100% occupancy. Interestingly, when the hormone concentration exactly equals the dissociation constant, exactly half of the receptors are occupied, making Y equal to zero point 0.5. Before we move on, let us see this with a concrete example. Suppose a patient's blood test shows a circulating hormone concentration of 4 times 10 to the negative 9 molar. Laboratory studies show the dissociation constant is 1 times 10 to the negative 9 molar. We want to find what fraction of receptors are bound. We plug these given values directly into our fractional occupancy equation. Because the powers of 10 are exactly the same in all terms, we can factor them out, leaving us with simple whole numbers, 4 divided by 5. This gives a final answer of 0.80. Physically, this means 80% of the cellular antennas are actively receiving the signal, indicating a very strong cellular response. Now that we have used this formula to find occupancy, let us look at a second example from the perspective of a pharmaceutical scientist. The scientist is designing a synthetic hormone drug with a known dissociation constant of 5 times 10 to the negative 10 molar. They want to achieve exactly 90% receptor occupancy to trigger a healing effect. We are asked to find the required hormone concentration in the blood. We set up the exact same fractional occupancy formula, plugging in 0.90 for Y and our known KD. The final answer, after solving, is 4.5 times 10 to the negative 9 molar. Let us break down exactly how we derive this result algebraically. So, we have our setup, but how do we actually isolate the unknown concentration? This brings us to the step-by-step derivation. We start with our fractional occupancy equation, where the unknown variable is present in both the numerator and the denominator. To solve for this, our first mathematical goal is to eliminate the fraction entirely. We achieve this by multiplying both sides of the equation by the entire denominator. This brings the unknown variable up to the main line of the equation. Next, we distribute the 0.90 into the parentheses, multiplying it by both the dissociation constant and the unknown concentration. This gives us a linear equation that is much easier to manipulate. Continuing from our linear equation, our next algebraic goal is to gather all the terms containing the unknown variable on one side. We do this by subtracting 0.90 times the hormone concentration from both sides. Conceptually, the remaining 0.10 on the right side represents the 10% of receptors that are unoccupied. To finally isolate the hormone concentration, we divide both sides by 0.10. Mathematically, dividing by 0.1 is identical to multiplying by 10, which increases our constant by 1 order of magnitude. This proves our final required concentration is 4.5 times 10 to the negative 9 molar, guaranteeing the drug works effectively. Now that we have calculated the binding mathematically, let us visualize this process. On screen, you are looking at a schematic of the cell membrane. At the top, outside the cell, you can see blue triangular molecules representing the free hormones or ligands floating in the bloodstream. Embedded within the gray cell membrane are Y-shaped surface receptors. Notice how the shape of the hormone perfectly matches the receptor, illustrating the lock and key mechanism we discussed earlier. When they bind, they form the hormone receptor complex. Following the arrow downward inside the cell, this binding event triggers the glowing starburst, representing the final cellular response. This diagram beautifully summarizes the entire translation process. We have covered a lot of ground today, so let us review the key takeaways. First,
Hormone receptors are the vital translators of the endocrine system, turning floating chemical signals into actionable cellular commands. Second, they operate on the principles of chemical affinity, where the dissociation constant dictates exactly how tightly a hormone binds to its target. Finally, by understanding the mathematics of fractional occupancy, medical professionals can accurately predict cellular responses and design life-saving endocrine drugs. You now have a solid, mathematical, and intuitive grasp of how cells listen to the body's chemical messengers. Great job!